Welcome to the Solar Podcast. I'm Tim Montague, your host. Today, my guest is Dan Leary, founder and CEO of Denowatts Solar, a solar monitoring and data analytics company. Welcome to the show, Dan.
Thank you, Tim. It's great to be here.
I am excited and flummoxed to learn about your technology. And it's not often that I run into technologies that I struggle so much to understand, but I think this is a great opportunity for you to tell the story of Denowatts and explain to our viewers why performance monitoring is so important and some of the challenges with the existing technologies. Before you tell us about Denowatts, tell us about yourself. How did you get interested in the renewable energy industry?
Oh, back in 2006, I was looking to do something with my career, and I had just left the Army at that point, and renewable energies was really coming into a lot of markets, and it was a passion of mine, something I'd studied in college, and got together with some great partners, and built a clean energy company. And then helped spun out with other partners a hardware company in the space. So I've really spent the time since 2006 in solar, been very passionate about it, and probably about 2013 decided to branch out and focus in on performance analysis and data to help advance the industry.
So I know just a little bit about your background, and you have an affiliation with PanelClaw.
Yeah.
You also were affiliated with Nexamp.
Yes.
Can you tell us a little more about those affiliations? Because I think this is important background for our viewers.
Oh, sure. So as I mentioned, the systems integration company, the solutions company is Nexamp. We founded and built Nexamp. Now it's a solar developer, and I have since moved on from Nexamp. And in the process, and so at some point early on, we also looked at other opportunities in clean energy, our partners, and we said, geez, we could probably do some innovative things with racking, because it was very early on in the industry. So we put together a company, called it PanelClaw, and have put a great management team in place to run that company and build it into a market leader that it is now.
Cool. So now let's talk about Denowatts. What is Denowatts?
Yeah, well, what is Denowatts really starts with why Denowatts. If Tim, data is a headache. We started Denowatts because owners and asset operators often had a hard time reliably and confidently understanding the performance of their assets. They often just didn't trust their data. Yet data is so important to the advancement of the solar industry, and it's so important to their bottom line. So we set out to innovate, and we innovated three things. First is we built a better benchmarking technology, the Dino Sensor. Second is we offer this as a managed service and provide data quality control to make sure that data is coming through. And then third is that we offer and communicate this through a business intelligence platform. The importance of that is to help take all this great insight that we're learning from the data and simplify the connection to the bottom line of our client's business. And we do all of this for less than the cost of a traditional weather station.
So let's compare and contrast. Today, many solar projects are monitored via a weather station and then a monitoring system like an Also Energy, which is one of the platforms that we have become familiar with here at Continental. What are the advantages of using Denowatts versus a weather station, or is it a both and?
Well, our service replaces traditional weather stations for reasons we can discuss later. We wanted to build a better benchmark, but most importantly is we built it because we're not a monitoring company ourselves. It might be confusing because we deal with data, but we're not. Monitoring companies have a lot of responsibilities. They ensure device connection, setup of the devices, reporting to industries. They do performance analytics, but they have a pretty broad role. It's a very difficult industry. And what we wanted to do is be exclusively focused on performance analysis and benchmarking, and we offer this as a plug-in service. So we're sort of like an app for your monitoring company. So when you use Denowatts, you're replacing a traditional weather station with our service in technology.
And can we reliably install Denowatts into, for example, the Also Energy platform? Is it a seamless integration, or is that complicated?
It is. No, that's a great question. It is seamless. We developed the technology platform to have a SunSpec protocol, so it's a common communication language, meaning, so what this means is that our devices report the data directly to the monitoring company. The monitoring company takes our data and runs it through their analysis and their interface. So our clients are generally logging in to their monitoring company the way they always have. The data is just coming from our service. In addition to that, we have our own interface, which is a business intelligence interface. We use Tableau, and that is how we communicate other things outside of and separate from the monitoring company.
So let's walk through performance monitoring at a very high level. There's a lot going on in a solar array. Once you energize the solar array, you're then clocking the kWh production of the array. The weather is variable from a minute to minute, hour to hour, day to day, month to month, year to year. So there's a tremendous amount of variation inherent in solar facilities. And then you have the added complications of things like soiling, degradation of the technology, right? The panels are starting to slightly degrade over time as they get irradiated with the UV radiation. It's breaking down the semiconductor foundation of a solar panel, right?
Right.
Very slowly, 0.5%, maybe 0.25% a year. How do you see through that fog? Because I think it is quite challenging, especially for end users, say behind the meter solar projects, right? The end user is looking at their data feed going, okay, this is what Tim Montague said it was going to produce on a monthly basis. And then I have the actual production data. And sometimes those line up. Sometimes the actual production exceeds the model. Sometimes it underperforms the model. And then I'm explaining to the customer, well, yes, it's just a model and reality is going to be different. So, but is there really a reality?
Oh, of course. So you brought up a few really good points there. Let me try and hit them one at a time. The first one is benchmarking. And I keep using this term, but let me define it just for a moment because some people might not know what it means. Benchmarking is a known reference or standard by which we're going to use to measure things. Like if you want to benchmark the length of a pencil, you use a ruler. If you want to benchmark the temperature of your refrigerator, you use a thermometer. So if you want to benchmark and understand, how do you measure your solar performance? The first thing is you need to figure out what technology you use to benchmark. Now, traditionally, we've used weather stations. Like you said, energy output is largely dependent on the amount of irradiance and temperature, along with the electrical characteristics of the site. But maybe this is an area where we felt innovation was most important to the industry, because the ultimate success or the ultimate score you can give a benchmark is how accurately you can predict the output of a solar array under any conditions. So that's why we developed our technology. I'll show you in a second. And when you can very accurately, or with low uncertainty, as a lot of engineers would understand, that measurement uncertainty being so low is how we're able to get exceptional analytics out of the site and understand if it's performing as expected, or if it's not meeting expectations, and then why.
Okay. Well,
Yeah.
let's dive in. Let's give our viewers a taste of what we're talking about here. What is the device, and how does it work?
Yeah, absolutely. So the Dino Sensor, which is the technology we developed, this is the Dino Sensor right here, and hopefully you can see that all right. It's about the size of a TV remote control. It sits between a couple of solar modules in your array. So let's say you have a 2 megawatt array. You might put 2 of these out in your array, replacing traditional weather stations. What it's doing is it has 2 pyranometers. These are taking irradiance measurements. It has a temperature sensor and a second plug-in temperature sensor. So these are taking module and cell temperature readings. And what's happening is that every 5 seconds, we're taking these measurements and performing calculations. Those calculations I'll talk about in a moment. But the really important thing about this technology is we remove a lot of the reasons why performance benchmarks go bad with traditional weather stations. The first is the form factor. It's got to be properly aligned with your module, with your array, or else you're not going to get a good benchmark. So just the way that it's been built, it has to sit between a couple of modules, or to the side of a module in the plane. Second thing is there's no wires running to this other than a small antenna. This is completely self-powered, and it transmits via radio. So it wirelessly transmits about a quarter of a mile line of sight, no problem. And it's self-powered. About an hour of charge on this will run the unit for several days. And the reason why that's so important is because a second area where benchmarks traditionally go bad is they don't put the sensors in the right spot. They put them where it's convenient to trench to, or which can sometimes be in a shady or obstructed part of the array. This sensor needs to be put in the sunniest part of the array. So because of these technologies and innovations we built into this, we're able to get a much more accurate benchmark from it.
Okay.
And let me come back to the two measurements I talked about a minute ago, the 2 calculations, because those are probably the most important part of this. This sensor is remotely managed by our service. So it's connected to our server. And when this gets deployed out to a field at your site, we'll actually program in your PV Syst model or your helioscope model into the sensor itself. So we're putting in the DC, the AC ratings, the dynamic and static derate factors, the inverter efficiency curve, et cetera. We program that into this. So as we're taking measurements, every 5 seconds, we're also running a computation of the amount of energy that should be coming out of your solar array. And we take that computation and report it out. That's called expected energy. So this comes back to your earlier question, Tim, about client asks, is this doing what it's supposed to be doing? Well, that expected energy is specifically the answer to that question. Is it performing the way it should under certain conditions? And this also has a second calculation that's being run in it. Not only are we running our client's energy model, but we're also running our own standard energy model, which is what we call comparative energy. The importance of running that model, as well as in every one of our units, we put in a standard energy model with standard D ratings, and we can use that to help compare different sites, apples to apples, against a known standard, hence the denominator, the Dino.
Okay. And tell me more about that known standard. How is that established?
Well, the known standard is established from our data. This whole innovation was driven, it's a data-driven design. So we didn't design this to be the ultimate pyranometer. We didn't design this for NASA. We designed this for solar asset managers and owners to best benchmark solar arrays. And in doing so, we're able to figure out, okay, given most common technologies, what is a typical performance level that anybody could expect from an asset? And we program that in and adopt that as our standard. So when somebody now comes in with a new type of technology, a bifacial module, or inverter level optimizers, or other technologies that optimize, and they're anticipating greater performance, well, they can see how that performance benchmarks compared to a common known reference.
Okay. You mentioned bifacial modules. Is there any particular challenge with bifacial?
Well, with bifacial modules, in order to come to the expected energy calculation following, as it would be defined in your energy model, you need to be taking the plane of array irradiance as well as the inverse plane array irradiance. So there is a need to hook up a second pyranometer, which, by the way, plugs right into the back of this, and we put it off the back side of the array facing down. It's called an albedometer to measure the sunlight that would be reflected up to the back. So we use that in order to get to the expected energy calculations.
Right. Now, a weather station would typically have a pyranometer though today, right?
Yes.
And then the weather station is reporting back to the monitoring software what's going on with temperature and irradiance. How is that different than the data that the Denowatts is collecting?
Well, it really is the same type of information, but what's different is, irradiance is measured by pyranometers. As you know, there's different classes of pyranometers. There's much more research grade and advanced pyranometers, and there's much more lower grade pyranometers. So getting the sensors to be optimized for solar is the key to this. And typical weather station, you might have a large pole. It looks nothing like this. You'd have a large pole. You'd be putting maybe a global horizontal pyranometer on it. You'd have another pyranometer that might be in the plane of the array. You'd probably have an anemometer measuring wind speed. You'd have an ambient temperature sensor. You'd have a back of module temperature sensor. The reason why you have all that stuff is because that's how the industry's kind of traditionally grown. In order to be able to communicate your client how much energy their solar array is going to make, you have to go back and look at historic weather data sets. So you go back and look at universities, airports, 20, 30-year data sets to find out, well, what's the weather going to be like in northern Indiana? And from that, how much energy should come out of your array? So our whole thing about the innovation of the benchmark is that, well, that's helpful when we're putting together an energy model, but those types of weather stations where you're getting ambient temperature and wind speed and et cetera, that's not necessarily the best way to accurately benchmark solar.
So if I understand this correctly though, the critical piece here is that the Denowatts knows what the array should be doing, right? It's got all of the stats of the array, and then it is collecting in real time the same experience, so to speak, that the array is experiencing. And then from that, you should be able to determine how the array is performing. And let's talk about performance monitoring. What is that exactly, and why is it so important?
Well, so understanding the predictability of solar assets is key to underwriting them financially. I'm sure everybody can understand that. If you can't tell a bank how much energy your array is going to produce, then why would a bank lend to you? That's the nature of the industry. So being able to accurately put the energy model in front of experts to have them understand, you know, is this built correctly? Is it going to produce what we expect it to? Is a very important part of energy management, performance management. And then once the array is built, you know, if you're going to build an array and it's going to work perfectly for the next 25 or 30 years, and you know that, you don't need a weather station. You don't need to do any of this stuff because it's going to work perfectly. But, you know, point me to that person because it's just not necessarily what is the reality. Stuff happens, snow falls on modules, and we have to understand what the impact is of the snow. Shading hits modules, and shading grows over time. We have to understand what that shading looks like and what's happening to those losses. Inverters can turn on and turn off unexpectedly. Reclosers happen, hurricanes happen, you know, things happen. And that's why energy accounting is so important. And that's part of what our service is doing, is in helping to understand, okay, what was the potential for energy that could have been made, but more importantly, what happened to that potential? How much was lost to shade or to snow? How much actually made it into the grid? And what was our expectation for the performance?
Okay. And are you getting in the performance monitoring space then?
Oh, absolutely. As a plug-in service, again, what we're providing is the benchmark, the yardstick, if you want to call it that, by which the monitoring companies, the independent engineers, anybody that's a stakeholder in an asset can use to understand and measure the performance. But also we're providing this analysis level, the energy accounting, the benchmarking. Is it doing what the model said it was going to do? And then most importantly is this, like I was talking about, the business intelligence interface, and helping to, you know, taking the questions that are being asked by all different stakeholders and helping them to understand with in real simple terms, images, how to connect that data insight back to their bottom line.
So you described Denowatts as an app for the monitoring companies like Also Energy. Is there an opportunity though to go direct to customer, so to speak, or is it always going to be the case that you are wanting to plug into some other ecosystem that is creating tools to look at what's going on, for example, with modules, inverters, strings, panels,
right,
etc.?
Yeah, and all that stuff is why, you know, the monitoring industry is very complex, and Also Energy does a great job. They're great to work with. A lot of our sites work with Also Energy. Typically, Also Energy is not our client. Our clients are owners and operators. So it might be the owners of fleets or portfolios. It might be the asset manager that is responsible for maintaining uptime and performance. And it could be any of the other stakeholders involved that want to specify Denowatts and be involved with a project, if that helps answer the question.
Yeah.
I should also say, sorry, Tim, a lot of, about half of our sites are retrofits, meaning it's been an operating asset, and for whatever reason, the hardware, the weather station malfunctioned, and they needed a replacement, or it didn't have one in the first place. And the other half of our sites are just new installations, where we're working through the commissioning and startup process and the capacity testing with them.
Okay, let's walk through that process real quick on retrofitting a Denowatts into an existing solar array. Let's say it's a small, you know, CNI 300 kW ground mount,
Sure.
Roof mount for that matter, right? But let's just say ground mount. You're gonna install the device,
Right.
right? One or two. On a 350 kW project, would you install more than one?
we like to always install 2 whenever possible for redundancy.
Okay.
When a site is at 300 kilowatts, that might qualify just for 1. But most of our sites range from, say, 500 kilowatts up to 50 megawatts is what's typical. But that
Sure.
being said, if with a single Dino, like I said in the beginning, it's still less than the cost of a traditional weather station. So the way that we get started with that client is they'd come to us to our website, call us up, and we'd send them an order form. They fill it out, and then we put a kit in a box, and that kit consists of a gateway, which is this device right here. It gets mounted with the monitoring equipment. It gets connected to an Ethernet switch. So we're sharing the Ethernet connection and the cell modem with the monitoring company, and a 24-volt power source. So really simple setup, mounts right on a DIN rail in your typical DAS enclosure, data acquisition system enclosure. And we put an antenna on it. And now this is going to be how all the data gets communicated into the monitoring company. So this is the data feed in. And then the second part of that kit is the sensors itself. And let's say that we're going to send out a couple sensors with that kit. You would take these 2 sensors, and the installer would pop them in. They literally take a few minutes to put each one in. It's just that simple. And then we have a commissioning process. And this is where so much of the uncertainty of benchmarking gets wrung out of the process. This is where a lot of the innovation is. Even though it seems subtle, we have to make sure that these sensors are properly aligned with the array, and that the data quality coming in is good. So because it's wireless, it's a connection that's going to come through an XB radio. It can shoot a long distance, but we want to make sure the data is going to come in reliable. We want to make sure that our sensors are reading the same value within tolerance. And we want to make sure that the temperature sensors are set up correctly, and make sure that all the data is coming in as expected. So that's a data quality function that happens right at commissioning. And once we start to receive the site generation from the site, that's how we understand and confirm that everything's properly set up and ready to benchmark.
And what if the irradiance measurements from the Denowatts differ than the irradiance measurements from the weather station? How do you decide which is the better measure?
Let's see. So some of our sites do have both Dino sensors and weather stations. Again, our service replaces traditional weather stations, so there's that. But here's an important thing I'll say about calibration. Denowatts is one of only a couple I know companies that work in this space that have what's called an ISO 17025 accredited calibration accreditation, excuse me. So 17025 is the world's leading standard for calibration excellence. It's a big, thick manual and standard that outlines every aspect of testing and calibrating sensors like ours. So we achieved this accreditation earlier this year. It's by an international and independent testing and accreditation body, and it's something that we maintain. What that means for our clients is that they can know that our calibration coming through our sensors is absolutely managed and the top rated calibration in the world. Our measurement uncertainty for a typical sensor is about 1.1 to 1.2% as they go out to the field. That's in alignment with all of the very high end and great pyranometers that are often used in industry and academia to measure irradiance. So even though it's as a service, and to your question, what do you do when the measurements are different? When we send this out, we have a service guarantee that says that this is within 1.1% of measurement uncertainty. And if we find there is a substantial difference, we can do a lot of things to work with the owners to understand and rectify if necessary. It's certainly simple to send out another sensor and try that. Alternatively, if we'd encourage them to take their other pyronometers and send them to an independent calibration lab to make sure that they were reading properly.
Got it. Earlier you mentioned SunSpec. Where does ISO and you also have an IEC standard? How do those play relevant to SunSpec?
Oh, yeah, so well, SunSpec is a really good organization. They're innovating by trying to get common standards for all these devices that have to talk to each other, and really good group of people, and they've made some great progress in the industry. We are one little piece of that with our, I think they would call this a weather station or a MET station. And what that just means is that we built a Modbus map, which is the way that monitoring companies will get the data from our device. So SunSpec really talks about interoperability of devices. The second standard you mentioned is the IEC, which is the Inter-Electrotechnical Commission. It's an international body. And a few years ago, they published a 3-part standard called 61724. So there's a -1, -2, and -3. Combined, it's about 300 pages of absolute incredible detail about part 1, how to monitor, how to set up sensors, what sensors do you need, and part 2, how to conduct a capacity test for a solar asset. How do you set everything up to do a definitive time period capacity test when you build a site and know that it's doing what it's supposed to be doing. And then part 3 is how to do energy reporting and accounting. And it was put together by a very large international group. It's excellent. It's not perfect. Our data doesn't agree with everything they say in it. But here's the big beef that we have with it is that it's perfectly set up for a 20 megawatt solar array. And it doesn't necessarily, the standards that are in it are standards that I'd like to see every solar array adhere to, because it's gonna help every solar array, but it's just not feasible. To do some of these standards properly, you could be $20,000, $30,000 into sensors and equipment for MET stations, and that's before you have to go and do the analysis and everything else that has to come with it. So our innovation with Denowatts is to figure out how to work with these standards, embrace the standards, not agree with everything that's in the standard, but to take those standards and scale them down to assets to your 350 kilowatt ground mount site that otherwise might just forego having a weather station because it was too costly to try to adhere to those standards.
Okay. So back to our example, though, of retrofitting in Denowatts into a project. You're adding the sensor, you're adding the gateway, and then you've got this additional stream of data or a new stream of data. If you didn't have a weather station, then you're just now seeing much more about what's going on with the array. Mm-hmm. Does the system, how does the user interpret the results of what the Denowatts is reporting?
Perfect question. Can I switch over to some visuals to help show that?
Yeah, let's do that.
A picture is worth 1,000 words. And let me just set that up right here. Okay, you can see my screen all right?
Yep. Excellent.
First thing is how to interpret the results. What do you tell your clients, Tim, when they see the results coming in? First thing is with benchmarks, there's, in our view, there's really 4 different benchmarks. First benchmark is what's called predicted energy. And this is actually right out of the IEC standard I just talked about. Predicted energy is how much power would come out of, or how much energy would come out of your solar array in a given average meteorological year. It's called a TMY 50, a P50 year, using typical meteorological data. So these are historic data sets. And that's the number that you'd probably put into your pro forma, because that's what a typical year would produce for energy. The second one is your expected power. And let me just show you over here on the screen. Here's an example site that I just pulled up yesterday. And this is a basic interface we have to help clients understand performance, but it's just sort of the beginning, and there's a couple important things to show here. So in this case, in the last week, the client made 114% of what was predicted, or what was the average that they would have made. So it was a slightly sunnier week than typical based on historic. Right. The second benchmark, also out of the IEC standards, is what's called expected energy. And expected is defined as how much energy, simply put, how much energy is going to come out of your array given certain weather conditions. So given the amount of sunlight that we had during this period and the temperature that we saw of the modules, what we could say is that this site made 96% of what it was expected to. So there was a slight amount of underperformance, but that is an accurate way of understanding the performance of the electrical system. And then the next two benchmarks are not out of the standards, but these are benchmarks that we believe are very important as a company, so we deploy them. First one is the compared energy. So compared energy is very similar to expected, except we're not using the client's energy model. We're using a standard energy model, because we don't know if the client, well, I should say we kind of know, we do know, but we don't always know if the client's built a conservative energy model or an aggressive energy model. And there is a lot of variation with how designers build their energy models. So that's why we have compared energy. So it's one thing to say, hey, we're not meeting the expectation for energy, but is it because you have a aggressive energy model? And in fact, you're doing what you're supposed to be doing. You're doing as well as you could be doing. So that's the purpose of compared. And if you look down here at these two regressions, this blue line is a compared energy regression. The green line is an expected energy regression. This is our ultimate scorecard as a benchmarking company. These regressions are the measured power against the compared power that we simulated on the device. And what this tells you is, first, there's a very low measurement uncertainty, but the average person can look at this chart and say, wow, every dot is a 15-minute interval data point, and you're very accurately predicting over the week, given certain conditions, how much energy is going to be coming out of that solar array. So that linearity of that regression is really our ultimate score. But what these two things tell us is that the compared energy was running about 94% as an index, while the expected regression was running about 96%. So what that means is, in this case, the expected, or the energy model, was a little bit more conservative than a typical energy model might be. And really the solar array is producing about 94% of what's typical. And sorry, okay, one last benchmark I should have put on is learned. Because once we've had the predicted based on typical meteorological years, we've had expected and compared based off of energy models. But now let's understand how your array is performing compared to itself. When we commission a solar array, we know everything's working perfectly, we benchmark it. That's what we do at Denowatts. We understand, how it was working when it was commissioned back in May, and we track that. and we follow it based on on a week-to-week basis to understand, is it improving, is it degrading, and that forms the basis of so much of our analysis and energy accounting.
Okay. I still don't quite understand learned. What is the value of the learned product, so to speak?
Yeah, the value of learned energy, and this is where machine learning and AI algorithms come into the future of solar. And what we're doing right now is, energy models are not perfect. Historical data, weather data sets are not perfect. Climate's changing. Like a lot of stuff, it's good, but it's not perfect. But what we can do is, if we have a really great benchmarking system, and that's what the Dino technology does, then we can use that benchmarking with machine learning techniques to understand what a solar array, how it normally behaves. Maybe that's a better way to say it. Because once we know how it normally behaves, when it's not behaving that way, well, we need to flag that period and understand, well, was it from shade? Was it from snow? Was it from some sort of equipment outage? Or is there another sort of more subtle performance issue going on with the modules or something like that? So that's the value of learned energy. It's really
Okay.
to the day-to-day asset managers and people that are overseeing the operation of that asset.
Yeah. So one of the considerations in all of this is the performance guarantee, and we quake in our boots when we hear those two words, because no matter how good you are at installing super high quality construction projects, there are so many uncertainties in a solar field that we are very shy to sign on the dotted line of a performance guarantee. Talk about that a little bit, because at the end of the day, somebody is on the hook for the performance of a project, whether you're the facility manager or the asset owner. Let's say with a community solar project, right?
Yeah.
The community solar project is going to produce a certain number of kWh according to a PV model that the developer developed over the course of the initial life cycle of the project, and then they're hiring the best installer, buying the best equipment that they can afford, and putting it together, right?
Right.
And then reality strikes, and things happen. A squirrel chews through a wire, and all of a sudden you've lost a string, and your production is you're off of your model, right?
Yeah. Yeah.
And is this a Denowatts to the rescue scenario, or tell us a little bit about that?
Boy, it should be. Energy accounting is what needs to be happening in this case. So when the system's performing great, we know it. If the system's performing a couple percent under, we know it. And we like to try and get to the bottom of it. So we flag it. And then this comes back to maybe contracting and again, more business intelligence. When a system's underperforming, why? Because in a performance guarantee, I mean, in early days, somebody might have wrapped it and said, "Oh yeah, we'll take responsibility for all of these crazy scenarios you just described." But in reality, there's force majeure things that happen. The utilities can go down. We just went through hurricane season. A lot of sites had to shut down for a period. Denowatts knows how much energy was lost during that period because, again, we're doing fog computing on this, and we're tracking how much energy should have been coming out, even though the site's down. So we can tell them, yeah, you've lost this many megawatt hours due to the hurricanes coming through. But in our accounting system, that's flagged as that's a utility outage. There's a force majeure. Snow is a common one. we're tracking snow. So in our outage accounting system, if snow's detected, and this is where we use machine learning to help us with that, when snow's detected, we can see the underperformance due to snow. One of the things we can show you here in the slides is the shading map, because well, if there's underperformance due to shading, who's responsible for that? Is it the responsibility of the owner to cut the shading back, or was it the designer that didn't really account for shading properly in the first place? So, having that information sorted out in that level of detail is critical to get to the bottom of it, but it's also critical to help us learn and grow as an industry, and make sure that we know how to not make the mistakes that we've made in the past. And it's part of the growing industry.
Right. And I also want to revisit something you said about aggressive models.
Yeah.
Right. We when we're designing solar projects, we want them to produce as much energy as possible for a given amount of PV, right?
Right.
The kWh per kWp is an important thing, and it does impact the economics of a project. So we're incentivized actually as designers to be aggressive with our models. But of course that backfires if you're too aggressive and then reality is different and the project is perceived as underperforming.
Right.
How do you, what do you say to designers and engineers on the front end? Is there a playbook for being realistic, right? Is there a perfect approach?
Well, half of what you're describing is weather, and something that's unpredictable and changing, and all we can do is look at historic data sets. So choosing the right data set and understanding what different data sets mean is certainly part of that, to make sure that we're not getting too aggressive with maybe the financial part of the modeling. But the other part of it is, well, in the design part of the model, are we using the right inverter efficiency? You get pan files from every vendor that says, oh, use this data. It's going to give you better results, and more accurate results, I should say. So you have that aspect of the design. You also have things like ohmic losses. You have things that can ultimately impact the output. You have static losses, assumptions about soiling and snow, and how this is all going to play out. And really, our opinion is this is precisely where business intelligence is so important to the industry. It's not just charts and things that you see today, but when you need to be thinking about this, like, I have a question. I'm the COO of a company, and I have a question. I want to know how many photons we got, how many photons we converted to electrons, and how many of them made it out into the grid. And I want to understand how many photons we lost to the trees, how many photons we lost to the snow, how many photons we lost to inverters that were not having the reliability that we anticipated. And I need to see all that information in a screenshot, because I want to understand if I can be smarter about purchasing equipment. I want to understand if 0.5% per year is really the right number. I want to understand how temperature and hotter climates is impacting overall performance. And this is the case for business intelligence. And this is how we approach that. If I can answer your question that way. To us, business intelligence is saying, okay, I have a question. I want to know something specific. And there is a image that's going to give me that answer. It might be a chart, it might be a table, but it's going to be something that's going to give a real and apparent answer. Maybe I can show you a couple of these, because some of these come back to how do we come up and identify, do we have an aggressive model or a conservative model?
Okay.
And I'm going to just start at the top of show you a couple of quick screenshots from our business intelligence interface. So this is what our clients see. And
you have to reshare your screen. I turned that off.
Oh, all right. Thank you.
There we go.
You can see it now? Great. All right. A very important chart is taking all of those benchmarks we talked about a few minutes ago, and how much energy do we generate compared to our 3 energy benchmarks, predicted, expected, and compared, and put them on a chart. This is an aggregate right here of somebody's 60 megawatt portfolio across 15 different states. And that's what you'll see in a lot of this is understanding, you know, well, I can see from this chart that we anticipated modeling high in the winter months, and we under modeled in the summer months. And you know something, if I went back and looked at the last 3 years of data, I'd see that's pretty typical. So maybe we should be a little bit more aggressive in our summer modeling. As an example, in the next chart, we look at that same portfolio and say, okay, well, what were our key performance indices? Did we hit our target? So when sites were in service and fully working, our electrical performance was almost exactly what it was supposed to be. It was, call it 1.01 of a factor. So we made about 1% more power for our designs that we anticipated across the entire portfolio. Now, that being said, after you account for downtime, it was about 0.987. So we had some losses. That availability, by the way, was a 0.98% availability. Each one of these months represents the aggregate of the portfolio we're looking at. The gray is the measured generation that came out of the site. The green little bands in there represents losses due to shade. The blue represents losses due to snow, as you can see them in the snowy months. And the red represents outage losses. So you can see, you know, of your total potential, how much energy you actually put into the grid. And another way to look at your outages and losses is in a tree chart. What sites had recorded outages and how much energy was lost at that site and why. So this is all part of the business intelligence. So you can sort of triage and say, geez, you know, these sites over here are where we're losing our profits. What's going on with those sites? Let's go take a closer look.
Each box is a site there, or I'm not sure what I'm looking at.
Yeah, I'm sorry. So each box in this case, and I redacted it obviously because all of our data is redacted. And each box is a specific site, and the number associated with it is how many kilowatt hours was lost at the site. And if it's gray, it was undetermined, which is likely a hardware issue that we're waiting for the owner to identify what specifically happened. If it's green, it was shading. So this site right here has a shading problem, much more so than some of the others. And if it was blue, the blue boxes are the snow areas. So these two sites were hit harder by snow. So this is where we can start to understand, okay, where's our snow belts? What are the profiles for shading? And what do we want to be careful of in the future?
Great, thank you.
Yeah, absolutely. And I won't get into these next few slides too much, but if you're the energy modeler and your job is to put together the energy models, you'd want to do a post-mortem on, well, this is what the typical meteorological year weather pattern said, what actually happened. And this is where you see, well, we got less light than we modeled in the winter, but we got more light than we modeled in the summer. And again, this is across the whole portfolio of projects, or you can look specifically at an individual project. Same here. This answers the question, in what months are we more effectively modeling? In which months are we less effectively modeling? And this is a chart that kind of gets to your earlier question, Tim, about, well, how do we know if we're being too conservative, if we're being too aggressive, and how do we know what's been going on with the irradiance? And this particular chart looks at a handful of states, and it shows the irradiance levels that were observed or measured by the Denowatts system relative to what was expected in their energy model. So, for example, in Colorado, some sites didn't see, a few sites saw the amount of irradiance, effective irradiance that they wanted to see, and this is for the last 12 months. But a number of sites didn't see the amount of irradiance they expected. So, you can use that to inform maybe your future modeling, and so forth. But it helps you to be able to compare, because irradiance and weather data is so regionally based, that this sort of region by region comparison in real time helps you understand what's happening. And so that's just measuring irradiance. Then we look at your energy, your expected energy performance. So given the amount of sunlight and temperature that you had, how did the systems perform? And this is where you can see, okay, regionally, some, or state by state, or maybe portfolio by portfolio, some projects perform a little bit better than expected than others. But again, it comes down to expected. Do we have more aggressive models in certain areas and less aggressive in other areas? So there's a tremendous amount. And all this, you can drill down into it in our system and manipulate it and work with it to help answer your questions. And then the last one to show you here is, well, okay, forget about everybody else's model, but going back to the Denowatts standard compared model, how are we doing? What's the apples to apples? Look left and look right. We can see all our sites, but let's look at all of the other sites that are using Denowatts. They're all redacted, and let's understand. So our sites are blue, and everybody else's sites are orange, and they're redacted. And how are we doing? Some sites just perform better than others. So let's get to the bottom of why that's happening and understand it.
Well, so as I'm just thinking, this has got my wheels turning. If you're a portfolio asset owner, let's say you own hundreds of solar projects around the United States,
right?
You could actually compare and contrast site performance based on, for example, the equipment used. If you had, a certain manufacturer of inverters or modules, you could compare and contrast the performance of projects by who the installer was even.
Yeah.
So this gives you some very powerful analytics for comparing and contrasting projects against one another, right?
Yeah, I'll show you two examples of that specific point. One is part of our, again, our business intelligence interface is understanding the conversion performance, which is really the inverter efficiencies and ohmic losses kind of bundled together. But how well are we getting those photons and turning them into electrons? And so in this particular visualization, this black line right here represents the CEC inverter efficiency rating of the particular inverter that we're looking at for a site. And all the dots represent the actual conversion data point, the percentage of observed efficiency of conversion. They're colored differently depending on the temperature. And this helps us understand, well, are there some technologies that are impacted more by temperature than others? And coming back to your point about understanding the equipment out there, well, you start off this chart by saying, okay, where is my site? And you see your sites in this list. This is again redacted, so it's going to be hard for you to see because I made it that way. But if you want to look at, okay, I'm looking at a site, it's got a Power One Ultra 1100 TL inverter on it. I can look at this site, but I could also click, there's another redacted site right here that's also using that inverter. How's it doing? How are the sites doing that are using the SATCON or the PV powered or the SCOW or et cetera, the SMAs. So being able to put technologies and manufacturers side by side is really important part of data. And we do the same with on the module side. Same type of analysis, but this is looking at a week by week analysis of your performance index. Are we seeing the temperature coefficients that we expected? A given module might have a minus 0.45% power loss per degree Celsius. And well, using our machine learning techniques, what is the observed temperature coefficient? What is the observed derating of age derating of this module? And then compare that across a lot of different modules and sites that are being used in Denowatts.
Well, I don't know if this is going to be a thing, but you know, it seems like you're in a position of having a database that is extremely deep and valuable. You know, I think of DNVGL and PVEL, they're benchmarking services, right, on equipment. Mm-hmm. And now we're going to have, as this type of technology expands, we're going to have just a tremendous amount of data on the performance of these projects. Tell me what are your thoughts about that?
That's what the industry needs to continue to advance and continue. The whole key to getting, you know, there's that saying, junk in is junk out. If you want to have really good performance analytics and, you know, see it in this nice, you know, business intelligence interface and have it be meaningful, you have to make sure that the very first thing you do is start with the benchmark. You have to start with the technology and the approach and the process that is going to give you the very consistent, very predictable, very reliable result. So that's why we started here. That's where it all begins. Once we can consistently predict the output of solar and benchmark and analyze it, go through the accounting process. You know, you don't fault the inverter because there's shade on it or snow on it. You know, you have to pull all that stuff out through the accounting process, and then you can look at, okay, let's narrow it down. What is the inverter really doing? What are the modules really doing? Did the tracking technologies help? What was the return on investment of that? The optimizers, all these things. There's a lot of questions, and it's you know, getting to the answers. It's going to take time, and we're going to learn a lot more about this over the years to come. But yeah, you have to have a really good database and business intelligence system, which includes tools, the great data, et cetera, in order to communicate that. And I'm just going to go back to the very first thing I said about business intelligence. It's all about data mining and creating a simple way to convert the benefits of data mining into your bottom line as a business. And that's what we do.
I get it. And I like it a lot. There just seems to be so many applications beyond the obvious, which is the asset owners being able to really granularly monitor their project performance over time. But the equipment manufacturers also, for example, right? Because you're adding this whole layer of intelligence that isn't necessarily there. If I'm a string inverter manufacturer, say Selectria, right? I can gather information about the performance of my products depending on how they're installed. But it's the relative performance of the product, right?
Yes.
You need that extra information. Otherwise, you pretty much just have very crude up and down time and some internal measures of efficiency based on what's going on, what is the temperature, et cetera. But
It's
um,
we call it the common denominator. That's the beauty of the compared benchmark, the Denowatt. The
yeah,
Yeah, that's, and hence the name, the common
now
denominator.
I know now I know why Costa, I almost called him Nico again. Now I know why Costa was so excited when he started telling me about Dino watts.
Yeah.
Uh, so thank you, Costa, for the introduction to Dan Leary. We're
Thanks.
almost out of time, Dan. What else should our listeners know, and how can people reach you?
Oh, please come find us. Our website, denowatts.com, and you can get anything you need to get started there. We we love working with new portfolio owners and new asset managers, and we have some great programs to help you try it out and understand what it is before, sort of diving in with your first site. We're very easy to work with, and we love working with all the monitoring companies out there. We've had great success doing that. And to get started, it's just picking up the phone, 978-496-3460, my phone. I'd love to talk to you about performance. You can do it through our website, and we really look forward to working with you.
What is a basic installation cost?
Oh, the basic installation is for benchmarking a typical solar array with a couple of these sensors is about $2,000 for a 5-year service. So again, we don't sell hardware, we offer it as a service. And if you want to have the full analysis and performance analytics and the energy accounting that comes along with that, it ranges from $3,000 for 5 years if you're under a megawatt, and if you're over a megawatt, it's $5,000 5 years. So about $1,000 a year, and you can take your small utility scale project and give it what I would consider to be the best benchmark in the business.
Now, you said that you're not selling the hardware, so are you leasing the hardware then?
Yeah, our service is a data service. And when we ship this out, we maintain communication and control of all of them. These are, we don't transfer ownership of the sensors. The beauty of that is, unlike a lot of the way traditional weather stations have worked, where you're dealing with warranties and recalibrations and sort of a lot of things, this is just a sensor. If there's ever an issue with it, your service has a service guarantee, a data guarantee with it. We'll get you out a new sensor and swap it out, because again, we're not in the business to sell hardware. We're in the business to do performance benchmarking and data analysis. So making sure that your sensors are fully up and reliable and operating properly is really our #1 priority. Otherwise, the rest of this doesn't work.
Got it. Well, to our listeners, please check us out at cesnrg.com. We post the majority of our content there. Check us out on YouTube as well. Please subscribe to our YouTube channel. Give us a thumbs up, hit that bell so you get all of the latest content from Continental Energy Solutions. I'm Tim Montague, your host. Thank you so much, Dan Leary of Denowatts Solar.
Thank you so much, Tim. Great questions, and I look forward to talking to you soon.
All right. Have a great day, everybody.